Hello. That wasn't much of a break, but I guess we could probably kind of crank this out and get to it.
Don't forget to record.
Yeah, I just hit record. Do you guys see a little button in the top that says recording?
Yep.
Whoever's, thank you for, oh, Tina, was that you? Thank you for reminding me. I need to remind, I also
Laura.
saved, oh, that was Laura. Sorry, Laura. I'm also trying to save the chat logs. Oh, hi. Hello. You know, this, I got to say, this format of video class is a lot of fun. It's fun later watching you guys doing your funny things inside of your apartments and stuff. Like, Tony, that sandwich looks really good. Kayla, I like your cereal bowl there. Okay, so it's fun watching everybody eat and do the funny things that they do. I know we have other things that we need to do with our day, so I'm not going to stretch this out. We're going to try to do a quick and hasty lab, and we're going to crank out those 3 problems, and my goal is to be done by 2. Sound like a plan? We'll keep our elements short and sweet. Do you have your sheet handy? Your sheet with gas names? All right. I would say if we want to be not too ambitious, it would be cool if we could do the following elements. Let's do hydrogen. So write down hydrogen on under your gas name on your sheet, okay? Let's do neon. Let's look at an incandescent bulb. And then let's look at the solar spectrum. I haven't actually yet tested the solar spectrum because I'm always prepping for these classes at night and I didn't have access to sunlight, but I'm hoping we'll be able to see the These are different types of spectra that we're about to look at. These types here are called emission line spectra. The incandescent bulb is going to produce for us a continuous spectrum. Continuous spectrum, you'll remember, is the same thing as a rainbow. And the solar spectrum is an example of something called an absorption line spectrum. So even though this is only 4 different elements, this is going to cover the 3 different types of spectra that we find in nature according to Kirchhoff's laws. Chrissy, are you having trouble reading that? Is that better for you? You guys all have some colored pencils and things?
Thomas, what page is it on?
It's 11-5.
11-5.
And I was hoping that you guys could put these elements down under gas name. We're just going to do 4. So 1, 2, 3, 4. Are we cool? All right. I'm just going to assume everyone's okay. Let's get to this. By the way, did you guys, no one answered my question. Do you have colored pencils? I'm just trying to gauge how prepped you guys are for this thing.
I mean, I got markers.
Yeah, markers are great, dude.
Crayons.
Oh, that's great. A box of crayons, totally cool. It don't have to be nothing fancy, okay? It just has to be able to make color. Kirill, if you're still there in the dark trolling us.
Yeah, so I'm doing the thing with a regular pencil and I'm writing the colors.
Okay.
And then I'm sending you the thing.
That will be acceptable, all right?
Okay.
So let's all go to, hydrogen's already in there. You guys can see that in my screen. Let's go to speaker view for a second. I've got my spectroscope. I've got my spectrum tube. This is hydrogen, is our first element. And let's share screen again. I'm recording, share screen, iPhone. So glad this thing works. Oops, I'm sorry. Share screen. Now, I happen to take a picture of hydrogen, which we could look at, but I don't know. It's kind of cool to try to do it live, don't you guys think? Or maybe I'm more obsessed with that than you guys are. Let me get your faces back here. Hold on. Are you guys seeing my iPhone right now? Are you guys there?
Yeah, we're seeing it.
Or here.
Sorry.
Yeah, you just got a voicemail.
I'm sorry?
Yeah, you just got a voicemail.
Oh, shit. Wait till someone starts sending me the real embarrassing text. Okay, so let's see if we can take a look at hydrogen here. You guys already know what to draw, right? What's the red line at?
$1.9.
That's electron volts. We should probably do this in, oh, guys, I didn't tell you something that's kind of important.
You forgot to mention that they're also like reversed
Yeah.
and that they're not.
So let's take a look at that, Carol. So there are two issues. On our handout here, not only are the directions reversed, you can see 700 nanometers is on the left, 400 nanometers is on the, 400 nanometers is on the left, 700 nanometers is on the right, but they're not actually using nanometers. They're using angstroms, right? And that's confusing because we're going to have to use the numbers to rearrange this. So let's just do this one nice and slow, and let's look at the hydrogen spectrum together. Notice if you look over here at the bottom, we have 600 nanometers on the right. Can you guys see my mouse as I move my mouse around?
Yes.
600 nanometers is on the right and 700 nanometers is on the left. What are the big ticks worth? Do you guys know how to do this? What you do is you take your interval, which is 100 nanometers. If I divide it by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the big ticks dividing 100 by 10 is 10, correct? The big ticks are 10 nanometers. What are the little ticks worth? Someone talk to me. 5 nanometers. Yep. So what is our wavelength here?
745.
Oh, hell no. Look, 700 is over. Yeah, 600 starts here. What is it?
655.
655. I love it. Okay, so what we're going to do now is, damn it, where's my colored pencils? I have some here. So, okay. I've got a red marker, right? So you'll go over here, and under hydrogen, we're going to put that's 6,200, 6,400, 6,600. Make a red emission line right there, right? Is that what you guys are doing? Okay. So let's get the blue line now. What's the wavelength of the blue line?
485.
485 sounds real good to me, Carol. And so make a blue line at 45. How about this violet line? Can you guys see my mouse? The violet line is what we want.
430.
430 is great. Okay, so let me make sure that I have. Darn it, you know what I forgot to do, students? I was supposed to be preparing And I didn't get out my color pencils. I have color pencils.
Por favor, póngame en la computadora a las 2 de la tarde. Ahí hay un link para vernos todos en Zoom. Exactamente. Sí. No, porque entonces yo lo puse a las 10:52 de la mañana. Usted va donde dice mi nombre, te dice la reunión de hoy es a las 2, por favor, le den al link. Si usted le da al link a ese número, le va a abrir. Y le va a decir arriba, Open Zoom. ¿Ok? Sí, por favor.
Okay. Sorry, I found my pastels. You like walking around my garbage heap together? So we got some pastels here. Do you guys have the spectrum of hydrogen? Can we move on? Give me a thumbs up if you're ready. Kayla, you okay? Kayla, you're muted.
Wait, where does the violet line go again?
So yeah, that's what I was gonna do. So if you remember, the violet line was at 430 nanometers. Oh shoot, that's paint. You know what, guys? The one thing that I forgot to do, and I just think about it now, is I forgot to get my colored pencils, which I have colored pencils somewhere. So likely I can't remember what color it is. All right. Well, I screwed up. I have a whole box of colored pencils somewhere, but I can't remember what it was. So what you got to do is you got to go over here in hydrogen. That's 4,200 and that's 4,400. You got to make your violet line right in there. Does that make sense, Thomas?
Yeah.
Sorry, that was pretty chaotic, but I'm still getting used to this it's very weird to teach a class from your home. When I'm home, I don't even feel like a professor anymore. I just feel like a ding-a-ling. So it's, okay. All right, let's see if we can swap out neon here. So hydrogen's probably really, really hot. Can we go on to the incandescent bulb next? Because I'll have to let that hydrogen cool down. Let's see if you can see the spectrum of an incandescent bulb. You guys see that?
Yes.
Hold on a second, guys. I've got it. There we go. All right. Let's slide this over. Take a look in there. Now, I can see this okay. Let me get a nice photo of this. Hold on. Sorry, bear with me. All right. We ready to do some Roy G. Biv? What range of wavelengths does red seem to span? Red kind of starts about there, right? What do you think, Tina? Sorry, Tina, I didn't hear that.
Yes, you're right.
What's that wavelength? This is like class. You know how sometimes I just call on a random person to freak you guys out?
Is that 610?
Yeah.
610, sorry.
610. That's what I want to hear. So, geez, man, I wish I knew where the hell my colored pencils were. look, we got to be quantitative about this, right? So you need to color in a range of wavelengths over here for your incandescent spectrum, right? So if this is the page here,
I would just like to remind everybody that this is going to be like this for the rest of the semester.
okay, Kirill, if that's a criticism, I'm sorry. If you can do a better online class, feel free to. It's the best I got, okay?
No, it's just like the hardships of online classes in general. It's not just.
All right. See what I'm doing there, guys? The important thing is it's a continuum. It's a continuum. Are we doing that? It's a range of wavelengths that go from 620 or so up to 700, right?
Yes.
All right. So how about orange? Orange is pretty narrow. Someone talk to me.
Is it like 580 to like 610?
Yeah. Yellow is particularly narrow. I think yellow, this is, let's see, this is, let me get a better photograph of this.
Oh, I can see it now.
It's tricky because I need multiple hands to do this. I definitely need those colored pencils. Ah, I can't breathe. All right, there we go. All right, so color in your colors. What about green? What range of wavelengths does green span?
Wait, did we figure out orange and yellow?
Okay, this is 550, 560, 570. Yellow is like 580. The CCD doesn't capture the colors perfectly.
Okay.
I want you guys to make yellow 580 to 590 or so. And then make orange 590 up to 610. Orange kind of spans this range from 590 to 610, and yellow is really narrow. It's like 570 to 590. Can you guys do that?
Mm-hmm.
The importance of the incandescent spectrum is that it's not emission lines. It is a smooth, unbroken continuum of color. You follow? All right, I can't see what you guys are doing on your papers. In a normal lab, I can kind of see where you're at, but I kind of can't see if you guys have this or not. Tina, you want to show me? Okay, cool. Tina, let's attack the green together, okay? I'm sorry, I forgot my colored pencils here. Green, 500 is usually very teal. You'll notice our CCD camera isn't picking it up so perfectly. So this is teal, but green kind of goes, oh shoot. Screen share.
510.
Sorry?
I was just telling you it was 510 where the green started.
Yeah, if you want to keep it simple, you can, sorry, my screen, I forgot to turn on my, oh no.
The phone died?
It's the lock screen. So what I need to do is I need to, oh my God. I need to go into this. I need to go to my display brightness. Auto lock. That's the issue. All right. Sorry, guys. Let's get rid of that photo. All right. If you want, you can make green from 500 up to like 570, okay? Now blue, it's actually kind of indigo. This looks purple, but it's somewhat indigo around 450. So fuck it, look. Just do blue from 450 to 500 and do purple from 400 to 450. Everyone cool with that?
Sure.
Keep it wicked simple, wicked stupid. Wait, from where to where? I missed that.
Sure. It would be so much good. I've got to figure out what the damn colored pencils is. Oh my God, I just found them. All right, here we go. So I want you guys to follow along with me here. Here's my little workstation. We're going to do this right. You guys see what I'm doing?
Yeah.
Okay, I've never even opened these before. Wow, this is actually nice. The crap. This ain't even a Roy. Oh, this ain't even a Roy G. Biv. Pastels. For nothing. They don't even have violet. I want a refund. Okay, so for your incandescent, you've got orange going from like 600 to 610. Yellow can be like, I don't know, 570 or so up to 560. Green starts at 500, why don't we? Let green kind of go up to here. You guys following this? Now to answer Carol's question, blue can go from like 450 up to 500 or so. Shucks, I gotta move that. Now I don't have purple because this box of crayons leaves much to be desired. But the violet, I guess I could mix red and blue to make violet, couldn't I? Let's see if I can make some violet here. They don't even have red, they just have orange. Let's see if I can trim this. Nope, that failed. Anyways, put your violet here, okay? I really should have gotten a box of colored pencils from the lab. I don't know why. That was the one thing I didn't think to do, guys. Okay, have we got this? All right. Let's now attempt to do helium. I'm sorry, not helium, neon. Well, this lab wasn't as smooth as I was hoping today, but it's mostly because I forgot colored pencils. That's the one thing I didn't think about. Notice the intense red color of neon. All right, wait till you see this one now. Okay, we got that? Now look, here's the deal with neon. Neon is not a continuum. It's made up of discrete lines, right? Any of these photos come out good? Well, these aren't great, but it'll have to, well, that one's particularly sucky.
Wait, is it neon or helium?
Neon, I said helium because I screwed up, I'm sorry.
Okay, and what's the fourth one?
Solar spectrum.
Okay.
Okay, so you guys can see what I'm doing down here, right?
Yeah.
It looks to me like we've got a bunch of red lines from, we've got 1, 2, 3 that are just after 650. So 655, 1, 2, 3. And then we've got 1, 2, 3, 4, 5, 6 between like 620 and 650. So let's go back to my dude here. Okay. Table. So we're going to attempt to do neon here. All right. Now, what did I do with that red mark? So we should do something like this. There was definitely a couple close to 650, right? 1, 2, 3. And then between like 620 and there was maybe like 4 or 5. 1, 2, 3, 4, something like that. Now, there was also a couple of orange lines in there, weren't there? A couple of orange lines, maybe 1, 2, 3, 4, between 600 and 610 or so. Okay, so go. So we'll take an orange one. 1, 2, 3, 4. You guys with me? Normally, I'd have you guys put more attention into the actual wavelengths, but considering that time is of the essence and we're straining, how are we doing on time anyways? What time is it? Oh gosh, it's already
140.
All right. And let's just throw a couple of yellows in there too. Let's just wing this because I didn't realize how long I was taking. I'm sorry about that. Me forgetting to get the colored pencils was my big mistake today. Okay, let's say that's good. I'm going to attempt to show you the solar spectrum now. And to do that, we don't actually have to use, we don't actually need to see the sun. And that's because the spectrum of the sun is actually reflected or scattered and preserved in the white clouds of the sky. So all we need to do to see the spectrum of the sun is to put our spectroscope up to a patch of white cloud there, and the spectrum of the sun will be preserved inside of that spectrum. So I'm going to turn my computer around here so you can see what I'm up to. I'm going to grab my spectroscope. I don't know if we're going to have sufficient resolution to see this, but we're going to try. All right, let it come into focus. Just give it a second. What do you guys see? Hold on. Let me get rid of the blinds here. A cloudy day is actually perfect for looking at the spectrum of the sun. Hold on, guys. I just need like a third hand to focus this and take a photo. Come on.
Perfect.
Ah, I think I got it. That was tough. Okay, hold on. Let's look at this together here and see what we got. Now, I don't know if you guys can see this, but you'll notice at first it just looks like the continuous spectrum, correct? You can see red going from 600 all the way out to 700. You can see orange around 600. You can see yellow here around 570 or so. You with me?
Right.
Now, my camera is kind of a sucky quality, so I didn't have quite a good enough camera. But can you see right there? Can you see that dark stripe? These are actually, this is a spectrum called an absorption spectrum. And these are dark absorption lines. I'm going to cheat a little bit here because, well, because my camera isn't very high resolution. I'm going to share screen. I'm going to go to the internet. And we're going to look up the solar spectrum at my old alma mater there, Boston University. They have a beautiful heliostat where they can take high resolution spectra of the sun. And this is what it looks like if you do it with a professional grade spectrograph. You actually see something like this. It looks like a pure rainbow, but there are thousands and thousands of dark absorption lines. You see that?
There's nothing on your screen right now.
What? Share screen. Oh, it's because it was the, I'm sorry. This is what the solar spectrum looks like. Can you see that now?
Yes.
So this is the spectrum of the sun. It's a complete rainbow with thousands upon thousands of dark absorption lines. And each of these absorption lines are related to different elements in the periodic table. Look how beautiful this is. If you scroll along to this thing, on a second here, you can actually scroll through these wavelengths and see all those dark absorption lines. Okay, so Carol's probably wondering, get to the point, Brendan, how do we do this? And that's a very reasonable thing to suggest. So let's get my screen mirroring going. And Britain. Okay. Here's what we're going to do. For our solar spectrum, we're going to start off by making a continuous spectrum, okay? So first we'll do red from like 630, and it's going to go continuous all the way to 700, all right? And we're going to draw in our continuous spectrum just like that. Orange will go from 600 to 630. We're doing the cartoon Roy G. Biv spectrum. Yellow kind of goes from about 570 or so all the way to 600. Then comes green. I'll actually do two different shades of green. I'll do a light green, dark green. Okay. Then we get to cyan. Cyan goes from like 480. I wish I had indigo. I can't get over how I don't have a purple marker. It's driving me absolutely nuts. Oh, I've got a purple dry erase. Yeah. See, now that's ingenuity. That's the kind of scrappy, daring do you need to do a lab at home. Never forget it. Now, what are we missing in our solar spectrum, students?
The lines.
The lines. So I remember seeing a nice dark line. I'm going to use a dark pencil here, right there in the orange. There's a handful in the green. All right, normally I'd want to be quantitative about this, but considering that we have 3 homework problems to do, we'll wing it, okay? There's a couple in red. And this is a solar spectrum. It's an absorption spectrum. You guys got that? So I've got my solar spectrum. I'm a bad student here. I'm doing a bad job. I wrote things in the wrong place. Here's my neon spectrum right there. My incandescent spectrum is a rainbow. And now that I have some colored pencils, I can do hydrogen proper. I had a red line at 656 nanometers. I had a violet line at 480. I'm sorry, I had a blue line at 486 nanometers. And I had a purple line here at 434. And this is probably the worst spectroscopy lab that I've ever seen in my life. And I did it. So I don't know, but that's okay. Hopefully yours will look a little nicer than mine. Can you guys see that? Please don't forget to put your name at the top of the lab. Don't forget to put AS1010 and your section number, whether it's 001, 002, 003. Oh man, I'm sweating. I got a little worked up there. Okay.
Oh my God.
Let's get off this thing here. Stop sharing my phone. All right. Students that I can see and that are willing to talk to me, is your lab complete? Did you get it done right?
Yes.
Okay. Now you guys know how to submit that by Blackboard.
Mine's a little jumbled.
You know how to submit that by Blackboard, right? What do you mean by jumbled?
I don't know, since I didn't have any colored pencils and I used regular pencil, it does look a tad bit messy, but there's the ones on the bottom. My iPad was bugging out. I couldn't really see the ones on the bottom of the page.
Who am I talking to right now? Because I'm a little confused.
Matthew.
Matthew. I'm sorry. I forgot. I clicked a button so that if you don't share your video, I don't see you. So you're hiding in the shadows somewhere, I guess. Okay, that's okay, Matthew. Matthew, I was going to say, if you want to hold it up to the camera, then if you want to share your video, I don't know if you're in your back room.
Yeah, no, I can now, yeah.
Oh, hi, Matthew. Now you've joined us. Matthew, you want to hold it up to the lens and just show me what you got there?
Yeah. So I've got this right here. I kind of had to put a little bit of a space in between the bars here, just so it kind of made a differentiation between which one I was labeling.
How did you do your solar? Okay, I can work with this. I understand times are tough. I'm not doing my job perfectly either. But I like this. I think it's fine. You have the colors written in. Can you show me your solar spectrum? How did you do the absorption lines in the solar spectrum? Did you make it negative white space?
That's the one that I didn't see. That's the one that my screen acted a little weird. Oh. And I couldn't see you. It focused on somebody else.
Oh, I see. Yeah. Matthew, to do that, you have to go to lock speaker mode. And you get that by double clicking someone's, speaker view is up at the top. And then you double click someone's face to put them into lock speaker mode.
Oh, okay. No, I see that now, yeah.
Matthew, let me share with you my screen again, okay? Hold on a second. There we go. All right, let me share screen. This is basically what the solar spectrum looks like. Can you see this here?
Yeah.
So, Matthew, since you don't have colored pencils, you'd have to do your incandescent, but maybe you could make the absorption lines. Do you see all these dark lines here?
Mm-hmm.
I don't expect you to put all of these in. This was taken with a very high resolution spectrograph. But maybe you could do 1 or 2 in the red, 1 or 2 in the yellow, and 1 or 2 in the green. But maybe you could leave them as negative white space, because if you think about it, the thing that you showed me, Matthew, was it was about like a black band, right? Which I'm cool with.
Yeah.
I understand that's the rainbow. Like, oh, actually, I got an idea. Let's look at an absorption line spectrum in black and white. Absorption spectrum, black and white. When astronomers used to take spectra before color photography, their rainbows would actually just look like this. So if you have mad good art skills, you might be able to actually use shading. Okay, this might be a little too ambitious, but do you see the spectrum on my screen here?
Yeah.
This is how astronomers used and still do have to look at their spectra. They prefer black and white cameras to color cameras because they're more precise. So they've made their absorption lines, this is a photo positive. So it shows the rainbow as a grayscale with some darker lines. But if that's too much for you, you could make it black and you could do a photo negative. So if I type absorption photo negative, I don't know if I can get anything. Anyways, you get my point, right?
Yeah.
I think you get my point. All right. Shit, I'm not having much luck there. Okay, so you have a plan for what you're gonna do?
Yeah. Do you mind if I see the spectrum just so I can see kind of like where the red goes, where the green goes, where the blue goes, like where it begins, where it ends? I can just shade it in.
Yeah.
There. Are there any?
Yeah.
Oh, I see what it is. Okay, so there's no markers on the bottom. I thought that there was.
Here, let's, are you still seeing my screen?
Yes. Yeah.
This is what the visible continuous spectrum should have looked like. Function F519. So what you can see is red kind of starts somewhere around like 630 or 640 and goes all the way to 700. Orange is kind of like 600 to 620 or so. Yellow goes from 560 to maybe 590. You know, our perception of color is psychological. These are all just wavelengths of light, but your brain doesn't think in terms of numbers. It thinks in terms of color feelings or whatever the hell. So your perception of yellow, what we think of as the color yellow, is a very narrow pass band from about 570 to 590. Green, you can just go from 500 to 570. Okay, Matthew?
Okay.
So block that as green. Blue, you could, if you want to get into indigo, which I think you should, cyan blue is kind of like 460 to 500. Indigo is 440 to 460, and violet is 400 to 440. One of the cool points to this exercise, students, is this forces us to kind of become familiar with the wavelengths of the visible spectrum. That's a cool thing to know about. You have to take my word for it anyways.
Does this work? For the incandescent bulb and the solar spectrum, I know it's a continuous thing. It's not lines, but I was drawing with my trackpad, so it was pretty hard. But
oh, am I talking to Peyton right now?
yeah, see,
Peyton,
I put the
get that. Let me put you in lock speaker mode. Hold on, stay right there, buddy.
all right.
Let me stop share. Okay, that.
Yeah.
Hold on, dude. That looks great. Look,
Okay.
under the circumstances, I love you all. You're all here with me. You're trying. I'm trying. None of us have control over the situation, so we're doing the best we can. Peyton, you could send that to me, and I love it. And by the way, I love your big map of America and back. That looks big too.
Man.
Okay. Should we crank out those 3 homework problems and get on with this? I can be a little long-winded, so forgive me. All right. Does anyone have a textbook handy? Or does anyone have the numbers handy? Because I've got a textbook right here.
54, 55, and 57.
Okay. Tina, do you have the problems? Okay, back to our homework. This is chapter 5, 54. Is that what you said, Tina?
Yes.
Do you want to read us the problem or should I do it? I didn't get that.
I'll do it, hon.
All right,
Give me just 1 second.
you got it.
Okay, number 54, radio station. What is the wavelength of a radio photon from an AM radio station that broadcasts at 1,120 kilohertz?
Now,
Second, I'm sorry, go ahead, hon.
no, okay.
The second part is, what is its energy?
All right, so we have 2 questions to answer. By the way, does anyone realize that I made a mistake during lecture today when I was talking about radio stations? I was not thinking clearly. Hold on a sec. I just want to make a correction to my lecture, if I can. Earlier in the lecture, I told you that AM stations broadcast in the megahertz range and FM stations broadcast in the gigahertz range. Now that I'm thinking clearly, I have no idea why I said that. FM stations broadcast in the kilohertz range. But it took this problem for me to remember my error. Do you guys notice that? Oh, well, well, just take my word for it. If there had been a ham radio operator here, there are people who get really enthusiastic about ham radios. They like to talk to the International Space Station, and usually it's grumpy old men that'll talk to each other over CBs, and you know, it's just it used to be a cool hobby, but it's now dying. It's a dying art. Anyways, a ham radio operator would have stopped me cold in my tracks and said, "What the hell are you talking about, gigahertz? FM stations use kilohertz." How many hertz is in a kilohertz, do you think? Who loves the metric system?
1,000.
Thank you.
I said 1,000, but I was muted, so he beat me to it.
Oh, yeah, sure you did. Okay. All right, hertz. All right. So this radio station, what kind of quantity is that again? What is this?
Kilohertz?
Well, that's its unit, but what are we measuring when we measure 1120 kilohertz? My question is not clear to you guys, and that's fair. We have to find wavelength, and we have to find energy. What the hell is this? What does 1120 kilohertz measure? It measures...
That's the frequency.
Thank you.
Yes.
I just wanted to make sure that you guys could identify that as the frequency without my help. I wasn't sure if you guys would recognize that. Okay, we need some formulas. Which formulas?
Wavelength times frequency equals speed of light.
Okay. And we have to solve for frequency. So I'm going to take wavelength and push it down to the bottom. Frequency is the speed of light divided by wavelength, right?
But we don't have the wavelength.
Oh.
It's the other, it's
yes.
Wavelength minus.
Clearly my blood sugar is getting low. It's wavelength is the speed of light divided by frequency, right?
Right. Yes.
Thank you, students. Geez, maybe you guys should be teaching this class. Okay. We have 3 times 10 to the 8 meters per second, right?
Yes.
And our frequency, can we put in kilohertz, yes or no?
Should it be 1 over seconds? 1 over?
Well, okay. We currently have a frequency of 1120 kilohertz. But 1/seconds is a hertz, right?
Right.
Is that okay? What do you think, Laura? I see you shaking your head.
So we have to change it into hertz.
Okay, and how do I do that?
Dimensional analysis. So you put kilohertz on the bottom and hertz on the top.
Yep.
And 1 kilohertz on the bottom equals 1,000 hertz.
Hey, you're pretty good. That was Laura, right?
Yep.
Are you good enough to do this in your head?
I mean, I should be, but
Huh?
I said I should be.
You just tacking 3 zeros on it. The frequency is going to be 1.12 times 10 to what power?
To the 6.
Beautiful. And that's hertz.
Yep.
And that, my friends, is 1.12 million cycles per second. That's what we want to put into our calculation up here. Because now it's in MKS units, correct? Okay, I'll just take that as a bigger time yes. So we'll calculate our wavelength then as 3 times 10 to the 8 meters per second divided by 1.12 million cycles per second. Can you guys do the punch and crunch for me?
I got 268 nanometers or meters.
Beautiful. Let's put a box around that because that's a classy move. Now we got to get the energy. What formula shall I choose? Actually, hold on. Let's just give everyone a second to finish copying. This lecture lab combo has gone quite a bit over what I intended it to, and I deeply apologize for that. I'm going to work on timing this thing out better. I need to have all my colored pencils in a row before I begin.
And preemptively, we should probably use the energy equals Planck's constant times frequency.
Sure. That sounds great. I'm going to do that up here. All right, so the energy is Planck's constant times frequency. For Planck's constant, we can use 7 times 10 to the negative 34 joules times seconds multiplied by, what am I putting in for my frequency class? You having trouble reading that, Angel?
Yeah, what did it say at 1.1210 to the what?
Do you mean here?
34. No, at the top.
Down.
Oh,
Nope, down. Right.
oh,
Yep.
6 power, sorry.
Okay.
Times 10 to the 6th. Is that a little better? That's why it's nice to see your faces, so I can kind of read the room, so to speak, you know? It helps me to figure out what's going on in your brain.
Is it 7 times 10 to the minus 34?
Yeah.
Oh my God, Jace, thank you. I was looking for my cap, and that's where it was. Okay. So what am I putting in for my frequency here?
1.12 times 10 to the 6 per second.
Per second. I like the way you said that. And what does that give us? What's 7 times 12? 77, 80. What is it? 84, right? So 7 times 1 is 7.84. Negative 34 plus 6. What is that? God, I'm faster in my head than you guys are in calculators.
Negative 28.
I got 28.
Yeah.
Wouldn't it be negative though? Because negative 34 plus 6?
Negative 28. We just heard negative 20. That's what we heard. All right, this is getting confusing even for me. Does everyone agree that it's power of negative 28?
Yeah.
Yes,
Yeah.
I got that.
Cool. What are the units?
Joules.
Thanks. Box it up. We're done. Direct application of today's lecture. I had a much cooler problem than this where we calculate the wavelength of WBRU. Maybe I'll start off next week's class with that.
Do we have to transfer that to electron volts at all, or no?
Oh, I was wondering if someone was going to ask me that. Do you want to know why I think that's a bad idea? This is a very, very tiny unit of energy. But I happen to know that by the time you get out to the radio regime, it's just going to be a stupidly large number of electron volts. So you don't really gain that much by doing it. Also, I'm kind of sensitive that I've gone over time here, and I'm worried that some of you are going to get really pissed off at me. So with that in mind, I should probably just get on to the next question, okay? Because I am trying to stay, I'm not very good at punctuality, but I'm trying to stay in the time budget here. So let's just leave this behind. I'm going to erase in a moment. Is anyone still copying? Okay, here comes Mr. Eraser. Okay. All right, what's our next problem, Tina?
Sorry, I was muted. It is number 55, UV photon.
Okay, read that out to us.
What is the energy in joules of an ultraviolet photon with wavelength 120 nanometers? 120.
And they also have a second part to the question, don't they?
That is correct. What is its frequency?
All right, frequency. All right. Are nanometers an MKS unit?
No.
All right. Jason, better convert that then. 120 nanometers.
Times division bar.
Yep.
Nanometers on bottom.
Yep.
Meters on top.
Beautiful.
And I forgot the conversion factor.
Nano means billionth. How many zeros are in a billion?
9.
So think on your feet. See if you can do it. I forgot too. I can't remember the conversion.
1 times 10 to the 9 meters on top. Or nanometers.
Is
Hold
1
on.
meter. But this is okay. There are a billion nanometers in a meter. That's true, Jace. But my personal favorite version is to flip the 10 to the 9 on top and make it -9. I like to do 1 nanometer is a billionth of a meter. And the reason why I prefer this conversion factor is because I'm a lazy bastard. And I don't actually need to put this into my calculator now because I can do 120 times 1 gives me 120 billionths of a meter. You see how I did that? Jace, if we had used your conversion factor of 1 meter as a billion nanometers, we would get the same thing. But mine was just kind of slick because I didn't need to compute anything. Okay, energy. Which formula do you want to use?
E equals H times F.
But we would need the frequency for that, wouldn't we, Tina?
So we would do H times C over the wavelength.
I love it.
The light just went on.
Yeah. Wait, do you mean like in the video or in your mind?
In my mind.
Oh, great. Okay, cool. That's an even better light. Okay. So 7 times 10 to the negative 34, the units of Planck's constant are joules times seconds, times the speed of light, 3 times 10 to the 8 meters per second, divided by the wavelength of 120 billionths of a meter. Well, you guys do the punching and the crunching, right?
1.7 times 10 to the minus 18 joules.
Sounds good to me. Can someone else from the class confirm that? Kayla, is that what you got?
We're not rounding.
Oh, what did you want to round it to?
1.75.
Oh, hey, we always round right, don't we, Chrissy? I hear you loud and clear, Chrissy, and I think you got the right moves. We're always rounding. But, so Chrissy, you agree with the power of 10? Where are you?
Yeah, that's what I got.
All right, then I like it. Put a box around it, that's a classy move. Let's move on to the frequency. Which formula do I want for frequency?
I got a
F
question.
equals C over wavelength?
Sure. I love it. That light is still burning bright. 3 times 10 to the 8 meters per second divided by 120 billionths of a meter.
Yeah.
Punch it up, kids. Punch it up.
2.5 times 10 to the 15th seconds.
Seconds?
Per seconds.
Yes, sorry.
Per seconds, because meters cancel with meters, and that leaves you 1 over seconds on the top, right?
Correct.
Okay, which is the same thing as 2.5 times 10 to the 15 hertz.
Oh, okay.
Right? Hey, we're making good time, guys. Well, I'm personally ready to move on to the last problem if you guys are. Laura seems to like that idea. Let's look at all your little faces for a second. Hey, oh, Tony's giving me the, by the way, Tony, you know, I realized in our last lecture after watching it, maybe I wasn't as supportive as I should have been about your whiteboard moves. I am so psyched that you like doing the whiteboard. If you want to take photos and submit that, that's okay. I felt like I gave you a lukewarm, oh, really? Oh, snap. You know, that's my fault, bud. I was psyched that you were putting those equations. I thought about that afterwards, and it's really effing cool. I think I was just so nervous trying to get this whole thing going that I wasn't relaxed enough to appreciate what you're up to. If you want to do your math on the whiteboard and photograph it, that's cool, you know? All right. Peyton and Matthew, how do you feel about me erasing? Are you still copying?
Yeah, I'm just copying down like the last.
All right. I'll give you a second then. Meanwhile, I'll get a fancy hat for the last problem. Okay, I got the 10-gallon hat on here, ready to do the final problem like a real cowboy. Yeehaw!
All right,
I
ready.
love astronomy. Okay, are you good?
Yeah.
All right. I'm erasing. All right, what's our last problem?
57.
All right, what does that say?
How many photons? Photons.
Yep.
Suppose that all the energy from a 100-watt light bulb came in the form of photons with wavelength 600 nm.
What does MN mean again?
Nanometers.
Okay, look. Have you guys ever seen those party light bulbs before that you can get at Home Depot? Do you guys know what a party bulb is? What color is 600 nanometers?
Red?
Orange.
Orange, right?
Orange.
So this is like a Home Depot party light bulb. It's like a laser light bulb that only gives out photons whose wavelength are 600 nanometers. And the light bulb has a luminosity of 100 watts. In our next lecture, I'll talk to you more about watts and energy per unit time, but luminosity, the luminosity of a light bulb is the amount of energy it emits per unit time. And the units are watts. 1 watt is equal to 1 joule per second. You guys cool with that? Okay, what's part A asking us?
Calculate the energy of a single photon with wavelength 600 nm. Nanometers.
Thank you. Nanometers. Okay, what formula do I want to use for that?
Sorry, I lost my formulas.
Okay.
Is it E equals H times F?
Well, you need the frequency for that, wouldn't you, Tina?
Yes.
But we don't have the frequency. What do we have?
We just have, I don't know. I'm stuck. Sorry.
The luminosity?
We do have the luminosity. The luminosity is 100 watts, right?
And we have the wavelength of 600 nanometers?
Our wavelength of 600 nanometers.
C times H over wavelength.
Yeah. So we want to use E is HC, Planck's constant times speed of light over wavelength.
Okay.
Are our units cool or are our units not cool?
Shouldn't we change nanometers?
Yeah, to what?
Would be 600 times 10 to the -9 meters.
Hey, not bad. So you basically just replaced nanometers with, you know that a nanometer is 10 to the -9 meters, right?
Right.
So you just did 600 times 10 to the -9 meters? Is that
Oh,
I like your moves there. Those some smooth astro moves. I tip my hat to you, madam. All right? So let's plug that right in the interest of time. It's 7 times 10 to the -34 joules times seconds times the speed of light, 3 times 10 to the 8 meters per second, all divided by 600 billionths of a meter. You know, most labs are supposed to take 2 hours. So if you think about it, we technically haven't gone over time yet. That's going to be my argument.
Is that 3 times 10 to the 8th or 10 to the 6th for the C constant?
That's 8. Let me make that clearer. Let me bring this closer. And let me make that 8 a little cleaner. So my hat's not helping here, is it? Let me take this stupid thing off. Trying to up my entertainment value here, you know? Okay, guys, punch them up for me. I like it when you do it.
I got 3.5 times 10 to the -19.
Sounds good to me.
That's what I got.
Can someone else confirm that?
That's what I got as well.
What are your units?
Joules.
Joules.
Box it up. Part A is done.
Yay.
Okay. Time for part B, but let's let everyone catch up here. I'm going to take a moment to click on all your faces in multi-view to see what it looks like. Peyton and Matthew are working. Tony's hands-free. Kayla's cool. All right. Jace has got his stuff. Matthew, you still writing down? Tina, you too?
I'm good, thank you.
All right. So let's just, Matthew, when you're done, let me know and we'll move ahead. Or give me a thumbs up or something. All right, cool. All right. Now we're going to move on to part B. What's part B ask of us?
How many 600 nanometer photons would have to be emitted each second to account for all the light from this 100-watt light bulb?
All right, let me translate that for you guys. They're asking for the number of photons emitted per second. Now, can you tell me what the units of my answer is going to be? What are the units of my answer in this problem going to be?
Per second?
1/2.
Well, okay, you're not wrong here. 1/2 is actually technically the correct answer, but I'm a little spooked because 1/2 are the same units as hertz. And when we talk about the frequency of an electromagnetic wave, we're talking about the number of cycles per second of our oscillation. That's not exactly what they mean here. And this might be a thing that would be lost if you were trying to do this problem by yourself. The units
Photons per second
are actually photons per second. And photons are a conceptual unit. They're not so much a real physical MKS unit. So whoever said that, yes, the units are going to be per seconds, but it's not going to be the frequency of an electromagnetic wave. It's the frequency of the number of little particle doodads that flow out of my light bulb per second. You know what I mean?
Mm-hmm.
Like, imagine if you stood at CCRI in the morning when all the students were walking in, and you had a little, like, you know, like a little number head counter, like the bar, like the people at the door of a nightclub have. They can count the number of heads that come into a club to count how many people are at the show. If you count people as they come through the CCRI door, that's also kind of like a frequency, because you're counting the number of heads that walk into your nightclub per minute or per hour or per second. Do you see what I mean?
Mm-hmm.
So, but it's not a frequency like an electromagnetic wave. It's not that oscillation. That's oscillations of electric field. Here we're talking about number of particle bits. How the hell are we going to do this? Okay. The 100 watts, they give us a sense of how many joules per second flow from the light bulb in all directions, right? So let's start with our 100 watts. 100 watts are the same thing of saying joules per second. What if we treated this like a big dimensional analysis problem? In other words, what if I tried to multiply by a division bar and I argued to myself, I want to start off with joules per second, and I want to end up with an answer that has units of photons per second. According to dimensional analysis, what units would I need to have in my intermediate step to end up with photons per second?
Joules would have to be on the bottom.
True. And on top?
Photons?
Yeah, I guess so. Man, if only I had a conversion factor from joules to photons. Like, how many photons are in a joule? How many joules are in a photon? You know what I'm saying there? Where am I going to
3.5
get a...
times 10 to the minus 19 on the bottom.
That's right. Remember that Jace is reminding us that in part A, we had worked out that one photon contains 3.5, right? Did we just have an aha moment there?
Yes.
Okay, cool.
I forgot my microphone was on.
Oh no, that's great. Wait, that's I can hear your voice. That's Samantha, right?
Yes.
That's cool, Samantha. I'm glad when I heard that aha, that was a satisfying aha for me. So I'm glad your microphone. So Samantha, where should my number go then? Top and bottom. What should I put top and bottom?
That 3.5 times 10 to the negative 19 should be on the bottom.
Exactly. And what goes on top?
1.
Exactly. Okay, guys. So take 100 and divide it by 3.5 times 10 to the minus 19. What does that give us?
I got 3 times 10 to the 20.
That sounds good to me. Which is a damn hell of a lot of photons per second flying out of a standard 100-watt light bulb. What does part C ask of us, Tina? Or Tina's still writing, I guess.
So photons per second is that's the proper unit for that answer?
Yeah, I would not recommend calling that hertz because hertz makes me think of the cycles per second of an electromagnetic wave.
Right.
These are not electric field oscillations. These are number of little orangey particles that are coming out of my light bulb per second. Does that make sense?
Yes.
All right, cool. So I'm just going to leave it slapped up there as photons per second, and you can do the same.
All right, sorry, I was on mute.
Oh,
Based on your answer to part B, explain why we don't notice the particle nature of light in our everyday lives.
In other words, they're asking us, why can't we see one single orange photon? Here's my little photon. Why can't I see one single orange photon? Let's have some suggestions from the studio audience about why I can't detect with my eye one single photon. What do you think?
Too small?
Okay, let's start with that right for a second. I just want to put these up here as we suggest them. One possibility is too small. Now, I agree with you, whoever said that a 600 nanometer wavelength is truly freaking small, right? Nanometers are billionths of a meter. On the other hand, all orange light is at a wavelength of 600 nanometers, right? So if 600 nanometers was too small to see, then we wouldn't be able to see any orange photons at all because all orange photons are at 600 nanometers. Do you see the conundrum there? It can't be that 600 nanometers is too small because our eyes seem to like looking at 600 nanometer photons as well as 500 and 400 nanometer photons. So I'm putting an X at too small. That's not good enough for me. Any other suggestions?
Is it because your brain interprets it as color?
Yes, your brain interprets it as color. You are not born knowing that you're looking at electromagnetic oscillations between 400 and 700 nanometers. You just see purple ice cream or something like that, right? But your brain doesn't need to know wavelengths to detect it. You can still see purple ice cream and get excited about eating it. Your eye can detect it. It's not about psychology or perception here. It's about, why can't I see one little particle doodad of light? We've already determined it can't be that it's too small.
Would it be because there's just so many photons?
Okay, let's take that as another possibility. Could it be that there's too many photons? Here's my issue with too many. There's too many minutes in the day, right? There's not enough minutes in the day, I guess. There's too many stars in the nighttime sky. There's too many grains of sand at the beach. But if I scoop up a handful of beach sand and I look real close, I can still see individual grains of sand. Just because there's too many of a thing does not mean that you cannot see individual members, right? There can be too many pine cones on a pine tree, but I can still detect an individual pine cone. There can be too many people in Times Square, but I can still see the individual people. Just because there's a lot of something, that's not an argument. That's not an argument. So I'm putting next to that too. I need another suggestion.
Are they too fast?
Let's try that one next. Okay, suppose we consider too fast. I agree, Jace, that light is pretty fucking fast. In fact, the speed of light, if you think about it, is 3 times 10 to the 8 meters per second. And Einstein's theory of relativity tells us that this is the fastest speed allowable in nature. So hell yeah, they're too fast. And yet, here's a problem with that. All light travels at 3 times 10 to the 8 meters per second. So you see where I'm going with this, don't you, Jace? If light was too fast to see, we wouldn't see any light. Ah! It's not that they're too small. It's not that there's too many. And it's not that they're too fast. Okay. Let's have a little thought question here. What if you could invent the world's tiniest Home Depot party bulb, okay? What if you could invent a quantum party bulb? A little microscopic, atomic-sized light bulb that was so tiny and so little that it would only emit 1 600 nanometer photon per second. So this quantum party bulb, which I guess is kind of like an atom if you think about it, right? This is part of our lecture today. If this quantum party bulb could emit 1 photon per second, what would the luminosity of that party bulb be? This is a thought question for anyone who thinks they understand what a watt is. What would be the luminosity of a quantum party bulb that emitted 1 photon per second? And don't say 1 watt, because 1 watt is a shitload of photons. Maybe this question is a little too rough, I don't know. I just want to know how many watts is a quantum party bulb that emits 1 photon per second? 1 photon of 600 nanometer wavelength light.
So small of a number that you wouldn't even acknowledge it.
In astronomy class, we are not afraid of big numbers nor tiny numbers. We have courage and fortitude. There's no such thing as a number too small for us to talk about because we have scientific notation at our side. I'm saying that you can give me a technical answer to this question.
Would it be 3 times 10 to the negative 20?
Say that one more time. You got it. What is it?
3 times 10 to the negative 20?
Yes, what are my... No, not negative 20.
No.
Almost. Guys, luminosity is the number of joules emitted per second. How many joules are in a single 600 nanometer photon?
3.5 times 10 to the minus 19.
that's why you threw me off with your 10 to the minus 20 shit. The energy of one single 600 nanometer photon is 3 times 10 to the minus 19 joules per second. That means this party bulb would be approximately 4 times 10 to the minus 19 watts. (10 to the minus 19 watts? I mean, the problem that we have here is a 100-watt light bulb. You can clearly see the light from a 100-watt light bulb. How many watts are in your refrigerator light bulb, like an appliance bulb? How many watts do those give off?
40?
40 watts. Very good, Tina. What do you think the wattage of a Christmas tree light bulb is? Take a guess. I bet it's like 1 watt or less.
Oh.
What do you, 12? Well, they're the ones that burn down your Christmas tree. Those used to be fun, right? But now they have Christmas lights wattage. I bet these suckers are like 1 watt. Did they tell us here? Would you agree with that? I'm wasting everyone's time here. Why can't I just tell you the fucking answer, right? Why do I have to be like this?
Hey.
Sorry. I don't know. I bet these things are 1 watt. Could you see a light bulb that was half a watt?
4 watts.
Oh, did you find that?
Yeah, I saw 4 watts.
Okay, 4 watts. So I was of order 1 watt, but close to it, okay? So, Tina, do you think you could see a light bulb that was, I don't know, half a watt?
No, I think the answer you're looking for is that our eye cannot see it.
Well, no, the question is, why can't your eye see it? I want the answer to that question.
It's too faint.
It's not too small, so it's not that answer.
Right? It's not too fast. It's not too many. It's too faint. But what does faint mean? Faint means like...
Not bright enough.
But a single photon, light bulbs can have a luminosity because they pump out photons per second. But a single photon doesn't have enough...
Wavelength?
Energy.
Thank you! Energy! There is not enough energy. It's a question about energy. See, you went through all the different physical parameters, size, number, speed, but no one thinks about energy. There's not enough energy in a single photon for your eye to get the stimulation necessary to make a spark in your brain. It's almost like, you know, mosquitoes try to land on your skin very delicately so you almost don't feel them. That's how they get you, right? A single photon does not have enough energy. So let's get our answer down, and then we're done with our homework and all the week's work. Part C is there is not enough energy in a single 600 nanometer photon for your eye to detect it. Yay. Let me write that a little bit clearer for people who are going to watch this later. All right. Yay, Tony, arms pumped, right? Let's have a talk about things. We're now done. We have now completed both our lab and our homework for the week. So you guys are going to have to go easy and forgive me. These first 2 lectures were not 100% smooth. We did learn some stuff, I hope, and we did get our work done, and that's cool, right? And I'm going to work on making this smoother. I definitely feel bad that it stretched on a bit. I think just not having a couple of things in place was part of it. None of the other labs are going to be that complicated. I did a lab yesterday on sunspots with my 1020 students, and it worked flawlessly. We got it done in exactly 1 hour. So I'm going to work on making this a little more efficient, okay? All right. Do you guys know how to submit these on Blackboard?
No.
All right, let's talk about that because I bet if there's other students who don't know how to do that either. So I'm going to share my screen with you. This will be the last thing I show you today. Here I am. I logged into my Blackboard. Can you guys see that? If you go to the lab section, the lab tab, so to speak, you can see over here my spectroscopy lab. That's the one we did. Now you click on that, and when it's out of 10 points, I think you can just, you can either take a picture of your paper. If you have a scanner, scan it. If you don't have a scanner, just take a picture with your cell phone or whatever you got to do. And once you make it a file like a JPEG or a PDF or a doc or whatever, you browse your computer and that's how you find it. Does that make sense? All right. And same thing with the homework. When you go to the homework tab, we just did chapter 5. By the way, I had printed out the questions for you guys. If you click on homework 5, number 5, you go into that tab and you can do a text submission or a browse your computer. Does that make sense? So get those up to me by the end of the, hopefully today or tomorrow, and I'll try to grade them right away.
That was my next question, the deadline.
Okay. In the forms that I get to fill out as the professor, I could choose when I constructed this what I wanted the deadline to be. Now, I specifically did not click that box because I just wanted this to be loose and flexible. If you got to make mac and cheese for your kids or something after this lecture, maybe it takes you a few hours or even a day to submit it. But here's what you cannot do to me. Do not be that jerk who tries to submit all of your homework on the last day of class, okay? If you do that, I will murder you. I'll delete you from my Excel book and I'll pretend like I never heard of you before, okay? So what I'm hoping is, in an ideal world, just kind of get it done. As soon as it's done on your paper, just snap a photo and put it up there and I'll give you your 25 points, okay? If you need to wait a couple of days, fine. If for some reason you don't upload it for 2 to 3 days, I'll still take it, but I can't. Next week we have another set of assignments to do and I get another assignments to grade. You know what I mean? I just don't want to turn this into a pig pile of shit. So if you can, upload it right away, end of the day, end of the week, Tina, whatever. I'm leaving the flexibility up to you as long as you don't screw me over. Does that make sense? All right. So you owe me 1 homework and 1 lab, which you should have done. Hey, one other thing that we got to talk about. At some point, I've got to figure out if I'm going to give you guys a final exam or not. Now, it is possible for me to construct some bitchin' 100-point multiple choice tests that you have to take on your computer there. And it may be that that is the right thing to do. On the other hand, this being a complicated circumstance, I want this to be a good experience. I want it to be fun. I just want us to hang out and talk and learn some science. So we could also double your midterm grade and just say the hell with it, we're done. Remember that your overall average is going to be an average of your exams and your homeworks and your labs. And because we're doing that all together, the homework and lab score should be like 100%, I hope. I don't know. Does anyone want to throw out some? I want to hear where you guys are at on that subject. I could see 2 arguments. Oh, please double it. I see a text right there that says, Brendan, please double it, LOL. Is that how people are feeling, or are people feeling like they want to take a test to try to improve their score? I got a thumbs up from Tina.
Having you double it would work better.
Yeah, double it.
Then it wouldn't be stressful, right? Then this could just be fun. So that's what I'm thinking. If I were you guys, I would just want to like log in, watch astronomy TV, copy a couple of things and submit it, and bam, I don't have to worry. This doesn't have to be a stress in my life at a time where we're all stressed out.
Yeah, if we were in the classroom, it would be one thing. But since we're online, I feel like I can't really, like you said, you don't really feel like a professor when you're home. I don't really feel like a student when I'm home. Like when I do better in school. So now that everything is online, I'm still like getting used to it. I feel like an exam like that big, like a final exam, would just be too much. Like I can do quizzes online, but like the final exam, it's like.
I agree too. And I have to admit, I've got some kind of unorthodox views about teaching. I don't like assessment. because I think assessment in itself is kind of suspect. I think if you hang out with people, you learn from them to the best of your own personal abilities. And sometimes like things don't click right away, and then you have one of those moments that Tina had where the light went on. And so I think that by hanging out together, by watching me run around my apartment, putting phones up to spectroscopes, that is a learning experience, and it should be fun and not stressful. So it sounds like the people that I've got online with me here are digging this double it thing. And I can see in the chat box some of the trolls that are hiding there that people are also agreeing with that. So that's probably what we'll do. Matthew, I completely agree with you. If anyone does have an issue with that, though, and feels worried about bringing it up to the entire class. Oh, Anna says she's hyped for the double. Woo, woo. Hi, Anna. That's okay, Ernie. That's all right that you don't have a camera on your computer. I'm just joking when I call you guys trolls. It's funny. It sounds like everyone's down with that. So if you do have any issues, send me a personal email and say, Brendan, I really wanted to take a 100-point final exam. I was just dying to do that. And if that's you, then I'll help figure this out somehow, okay? Because it should be your right to take that. But otherwise, we show up here every class, we learn some formulas, we talk about some science, and that's it. That's what we do. And then we get on with our lives, all right? So I had a blast hanging out with you guys. I'm gonna
quick question.
Oh, yep.
Did you post our midterm grades on Blackboard?
One of the classes.
What I got.
So there's Blackboard and then there's CCRI Pipeline. I did post your grades to Pipeline. Pipeline is here. Let me share my screen with you guys again here. I posted your grades here. Let's just go to CCRI. Your midterm grades, your midterm grade projection should be posted here if you log into like my CC, oh, it's called My CCRI now, I guess. Okay. There's Banner, and then there's My CCRI, and there's Blackboard. I don't really understand the structure of all this. And I posted your grades here.
If you go into the Students tab and you go down on the left, it says My Grades, and then you just select the semester from a drop-down box, and you can see.
Lucas, would you share your screen with us? Let me unshare my screen.
Let me see.
But I've seen that before. I've used it before. I just want to see what my actual midterm grade was.
The test grade.
Yeah.
All right.
Individually, separate from my actual midterm grade.
Oh, I see your, yeah. So I did put those scores in. If you go down here, can you guys still see my screen? Everyone?
Yeah.
Okay. Yep. So I go to my grade center, right? And I go to my full grading center. I don't know what it looks like on the student side, but here I've got the names of all the people in class. And I did try to put your homework grades in there. And if you, this system is hideously clunky and just horrible in every way to use. But you can see the names of the students. I'll hide them there. And you can scroll through here and you can scroll along. And there you can see your lab scores. You can check it all and make sure it's kosher with what your records have. So Chrissy, I think I did for the 1010 students put their exam scores up. I don't want to slide to them because I know you guys aren't too picky, but
I see it down the bottom. It's in yellow.
Okay. You got that?
Yeah. Awesome.
Any other questions or comments or things you want to say before we end today's class?
Yeah, so when we're posting our homework into Blackboard, can we use the Blackboard app? Like, do we have to use the browser version, or can we use the like the app? Because I'm using a tablet right now, so I wanted to know if I could just like.
This is an important comment that I want to address for everyone. Matthew, if you're typing up your stuff, I'm okay with that, but here's a big issue. You guys can see my screen right now, correct? Can you guys see my screen?
Yep.
This is a Word editor, a document editor like Microsoft Word, but they might have an internal one there to plug it into, or you might be getting a tablet. Here's what you cannot do, Matthew. If you're doing math, as we are, I do not want to see speed of light equals wavelength. Like, it can't look like shit. GTH, oh, I can't spell wavelength. LENGTH times 3. You can't do this kind of stuff, right? I don't want to see 3 times 10 caret 5 meters per second, because that looks like garbage and shit, and it's actually hard for me to grade. Now, you can use an equation editor, but you can use Microsoft Word, but you need to use an equation editor. So up here, I go to Insert Equation, and they even have Greek letters and things here. So watch, I'm going to do our formulas for today. If the speed of light is equal to, and up here in this drop-down menu, I can do lambda. Let's see here. They should have all the Greek wave letters.
Well, I did do it in my notebook.
Well, I guess I'm having trouble understanding, because if you did it in your notebook, why not just take a picture on it and upload it?
No, yeah, that's what I was saying. It's like I'm using my tablet, so I took a picture with the
Yeah,
tablet,
you can
so
use.
like,
You
but
can
I wanted
use
to know if
that.
I wanted to know if I could submit it like in the app, because it looked like when you went to where it showed like the spectronomy lab.
Yeah.
It looked like it was like a different format than the app, so I wanted to know if that was like the browser version or something. If I had.
Okay. Now I understand your question. Yeah, dude, just get it up there. As long as I can see something, I'll grade it, and I'll grade it kindly. Okay.
Yeah, the app is good. I just did it.
Oh, the app works. Okay, cool. Jace.
Courses. Okay, so we go to what course content?
Yep. If I share screen again.
Homework. Okay. Homework. What? Chapter 5.
Yep. We just did chapter 5, part 1. So hold on. My thing is freezing here.
And I'll do what? Start attempt. Right.
Oh yeah. By the way, guys, I forgot that you guys see attempts. Some professors limit the number of times you can attempt it. I don't see any point to that whatsoever. You guys have unlimited attempts. So if it gets botched, you just resubmit it. Okay. But you go to homework 5, chapter 5, and I think we'll look something.
Add file. Okay.
Cool. Any other questions, Jace? You had something you wanted to say?
You wanted me to remind you to save the chat.
Oh God, yeah. The chat logs are really, really funny, and they're also cool. And sometimes there's occasionally useful stuff there. So I'm trying to include that stuff. So I'm gonna save chat. You get like reading these chats afterwards. I have belly laughs. It's awesome. So okay, guys, I think that covers us for today, and I'll see you guys on Monday, right?
See you later.
All right, bye. Awesome hanging with you. Good luck. Stay safe. Peace out.